Hello. In this video, I'll be covering the basics of integrations. Let's start with definition of an antiderivative. If gx and fx are two functions defined on an interval I and the derivative of g is equal to f for all x belongs in the interval I, then gx is called an antiderivative of fx. The set of all antiderivatives for a function fx is called the indefinite integral of fx. The integral of fx with respect to dx gives rise to gx plus c if the derivative of gx is equal to fx and c is an arbitrary constant. Let's go with initial value problems. Finding an antiderivative of fx is equivalent to solving differential equations. That is, dy by dx is fx or y prime of x is fx. A differential equation with an initial condition y x naught is given by y naught is called an initial value problem. The most general antiderivative fx plus c of the function fx gives the general solution of the differential equation dy by dx as fx. The particular solution of the initial value problem is a function that satisfies both the differential equation and the initial condition. To find the particular solution, we must apply the initial condition and determine the constant c. And here in this table I have included some of the common functions, the integers of the some common functions. Please have a look at this and let's solve some integration by the method of substitution. Here we have an integral function dx by under root 1 plus 4x. So from the method of substitution, what we can do is let us consider u as 1 plus 4x and let's take a derivative on both sides. Derivative of 1 is 0 and we get 4 dx. Let us, and then we need the value of dx, which gives us du by 4. We can use this in the above by substituting 1 by under root u and dx is du by 4. We can bring the constant outside and 1 by, we need to find out this, and this is basically 1 by 2 times du, and from the formula we have x power p this one over here x is equal to x plus p plus 1 by p plus 1 plus c. So this is basically u power minus 1 by 2 dot du, which gives us by 4 times u power 1 by 2 by 1 by 2 plus c, that is 2 times of u power 1 by 2 plus c. And from the above we have u is equal to 1 plus 4x. Sorry, this gives us 2 plus c, which is there. And another approach of solving an integral is by parts. Integration by parts is a special method for integrating products of function. This method is based on the product rule of differentiation. Like if we remember from the previous video, we have when we have two functions u and v, the product of the derivation is u prime v plus u v prime. Let's take derivation on both sides. Let's convert the prime into the Lagrange. duv is equal to the u prime is du and v the constant and u and dv. And then let's interchange some functions, bringing over u dv to the other side and duv minus v du. And let's take integration on both sides, which gives integral of u dv as an integral of derivative of uv minus integral of v du. And here we see the integral and the differentiation gets cancelled, so all we get is integral of u dv equal to uv minus integral v du. So we are going to use this formula for solving any integration, so functions which have multiple parts in it, like for example, and we are going to solve them in the form in this order. So whenever we see a function which is a product of multiple functions, like a composite function, we need to consider this empirical formula order. So first we would be considering inverse trigonometric functions, and then logarithmic and algebraic and trigonometric, and in the last one priority would be given to the exponential functions. Let us apply this to an example and let's see how it works. So here we have an example. We need to find integration of log x by x squared dx. So here we have two functions, a logarithmic function and an algebraic function. So in an order, for our u would be log x, and if we consider the above, we need u and dv. So this dv becomes dx by x square, and we need to find, let's apply derivation on both sides for this, and L of x, which gives du has and dx by x. And here, since we have dv, we need to find v. Let's apply integration on both sides, which gives v, because this and this gets cancelled, and we know 1 by x square, if we consider this dot dx, and x power minus 2 dot dx, and this would eventually give us minus 1 by x. Okay, and now we have everything. We have v, we have u, du, and v. Let's take the formula from the above. So integral u dv is u v minus integral v du. So let's substitute everything. We have u, we have v minus integral v has minus 1 by x, and du is dx by x, which gives us negative log x by x. And taking the negative sign outside, we have 1 by x square dot dx, and from the above we know that the integral of 1 by x square with respect to dx is minus 1 by x. So using that, here we get log x by x minus 1 by x, and add the constant c. And now the second type of functions are the definite integral. Let us consider the function f, which is continuous in the interval a and b, and f is an antiderivative of f. Let's take this as g for let it be as f. Yep, antiderivative of the small f, that is derivative of f is f. Then the integral of fx between the limits a and b with respect to dx would give rise to fba minus f of a. And here we have some properties of the definite integral. So whenever we are given a function, the integral a and b, when we interchange the definite integral we have to use a negative, and the function would be the same thing. The only thing that changes are the limits and the negative sign. And when the limits are both the same, the function value would be 0. And if a constant is multiplied with the function, we can easily take out the constant outside and we can perform the operations. It would remain the same. And we can break up the definite integrals across a sum or a difference. And in the fifth property, uh, we can see that C is any number. The property here we must realize is that we can integrate a function over adjacent intervals has AC and CB, and we have to observe that C doesn't need to be between A and B. And for the sixth property, we have integral a to b f of x to dx, which is equal to a of b of ft of dt. The point of this property is to notice that as long as the function and the limits are the same, the variable used in the integration doesn't affect the answer. And for the constant, like if we see if C is any constant, then the output would be C of B minus A. And if fx is greater, the function value is greater than 0, and the value of x, if it lies between A and B, then the value of the definite integral between f of x dx a and b would be greater than 0. And let us consider there are two functions f of x which is greater than the second function gx, and the value of x is between a and b. Then the definite integral of f of x dx between a and b would be greater than ab of gx and dx. And similarly, whenever the function value is between a particular set like small m and m, and the value of x is between the limits a b, then we have this property. And the last one would be if we have the modulus of a of a function a b, it will be less than the modulus of a function between the limits of a and b. Let us take an example of a definite integral problem. So here we have integral rising from 1 to e of x plus 1x dx. So let us apply the definite integral to this, and using the property number 4, we can split this into 1e x dot dx plus 1e 1x dx, and this is x square by 2. 1 by x is log x by e square by 2 minus 1 by 2 plus log e minus log 1, e square by 2 minus 1 by 2 plus this would be 1 and 0. This is e square by 2 minus 1 by 2 plus 1, that is e square by 2 plus 1 by 2, there, or this. Thank you.